Hi everyone, I'm Chetan Kamath and I will talk about our work, batch proofs are statistically hiding. This is joint work with Nir Bitansky, Omar Paned, Santosh Devan, and Ron Nordblum. So yes, our result pertains to interactive protocols. There are two standard properties of interactive protocols, which are completeness and soundness. In addition, one can ask for other requirements. So two such requirements are succinctness and hiding, and our work kind of bridges two such notions of succinctness and hiding. So for succinctness, we consider batching, something called batching, and for hiding, we consider witness indistinguishability. So we bridge batching and witness indistinguishability. So let's define interactive protocols so that we are on the same page. So here we have a prover P and a verifier V who hold who both know some instance X of some language L. So we will be interested in the efficient prover setting where the prover also knows the witness W to the instance X. So for concreteness, you can think of the instance of the language three-colorability. So the instance X here would be an undirected graph, and a witness for this instance would be a three-coloring the graph. So how does the prover P convince the verifier V? So they talk back and forth, and in the end, the verifier either accepts or rejects. So in a non-interactive setting, like the amount of interaction is minimal, so the prover just sends one message to the verifier, and the verifier has to then accept or reject. So there is a setup involved here, but we will ignore this for this talk. So let's see what the completeness requirement is. It says that for any XW in the relation corresponding to the language L, the verifier should accept at the end of the interaction with overwhelming probability. Soundness, on the flip side, says that if the instance is not in the language, then a malicious prover should not be able to convince verifier that exists in the language. So we should not output one at the end of the interaction. So this comes in two flavors. So if we consider undone by provers P star, then we say that the protocol is a proof, since we consider statistical soundness. In a weaker guarantee of soundness is computational soundness, which holds only with respect to bounded adversaries. And we say such interactive protocols are interactive arguments. The same holds for non-interactive case. Okay, so let's look at the succinctness requirement, the one of the first additional requirement we actually asked for. So it says that intuitively can reduce the amount of communication between the prover and the verifier that it takes to convince. So we will be interested in succinctness in a particular form of interactive protocols called batch protocols. So batch protocols are simply interactive protocol for the product language LT. So the product language LT, it consists of instances x1 up to xt, and this instance is in the language only if all the individual instances are in the language. So x1 up to xt, they should all be in the language. So the interactive protocol for this batch language, the prover and the verifier, they share T instances, x1 up to xt. The prover, since we are in the efficient prover setting, will hold T witnesses, w1 up to wt. They interact, and at the end, the verifier accepts or rejects. So the completeness requirements now says that if all the T instantaneous pairs are in the language, then the verifier should accept with high probability. And soundness says that if there exists even one instance that is not in the language, then the verifier should reject. So again, we have both the two forms of soundness. So what does succinctness requirement say? It says that so the protocol is compressing with the rate rho or some rho less than 1 if the communication, shown here in yellow, is at most rho times t. So for simplicity, you can assume that the size of the witness is much smaller than the number of instances t. So now that we know what the notion of succinctness we are interested in, let's look at the notion of hiding we are interested in. So intuitively, hiding says that the protocol should not reveal information about the witness. So verifier should not learn information about the witness. So the standard notion of hiding that we want to consider is zero knowledge. But here, which says that like the verifier should not learn any information about the witness other than the fact that it's in the language or not. So the notion that we consider in our work is a weaker notion called witness indistinguishability. So for defining witness indistinguishability, or WI for short, we need to first define the view. So here we will consider honest provers. We will restrict to honest provers, and the view of the honest verifier, and the view of the honest verifier is, as the name suggests, is whatever it views in the protocol. So it would consist of the instances, the messages, and also the internal coins of the verifier. So here we have two views. On the top, you see the view of the verifier when the prover uses a witness W0, and at the bottom, you see the view of the verifier when the prover uses a witness WI. So witness indistinguishability, WI, says that these two views should be indistinguishable. And this is a worst case guarantee. It should hold for any X W0, W1 in the relation. And so we say that the witness distinguishability has error epsilon W1 if the distance is epsilon W1. So in this talk, we will be interested in a strong notion of distance, that is statistical distance. So we will consider statistical WI protocols, or SWI. So yeah, for just concreteness, so at the top you have the prover using a particular tree coloring, and at the bottom you have the prover using a slightly different coloring, but still valid. And SWI requires these two views to be statistically indistinguishable. Okay, so now we have all the definitions that we require for our talk, and yeah, so we will see. Let's just see what is known about these properties. So let's look at succinctness. So let's consider the class UP. So UP is the subclass of NP where which consists of the problems where the witnesses are unique. So these constraints contain interesting problems related to factoring, for example. So what do we know for UP? So we actually know that they have batch proofs. So they have batching. They support batching in the strongest sense. So this was established by through a series of work by Reingold, Rothblum, and Rothblum. And what about NP? So through a recent line of work, we know that if we are happy with the relaxed notion of soundness, that is computational arguments, then we know that NP has non-interactive, even non-interactive batch arguments. And we know this from standard assumptions. So for example, the work of Chaudhary, Jain, and Jain showed that NP has batch arguments, non-interactive batch arguments from LWE. However, we don't know much about batch proofs for NP. So in fact, like there is a related notion called instance compression. It was shown by Drucker that NP is unlikely to support instance compression. So you can think of batching to be witness compression. So like a related notion of instant compression is unlikely for NP. So that was about batching. So what do we know about SWI? So UP, the class UP, trivially satisfies SWI. So you can just think of the interactive protocol where the prover sends the witness over. Since there is only one witness, all the views, they look similar. So one would think that the class SDK has like SWI proofs. But I recall that we are interested in SWI proofs where the prover is efficient. but not all problems in SDK are known to have efficient prover. However, there was a work by Nguyen and Radan who showed that if we take the intersection of SDK and NP, then it does have SDK proofs with efficient verifiers, and therefore it also has SWI proofs. So that is all we know about batching and SWI. And given the state of affairs, what we ask in this, what we explore in this paper is what happens when you assume that NP can be batched. So we show two results. So the first result says that if you can batch proof NP statements, then NP will also have SWI proofs. So again, it says succinctness for NP implies hiding for NP. So this result is with caveats, which we'll see soon. And you can interpret this as both as a positive result and a negative result. The positive result is says you can construct to construct SWI proof, you just need to construct a batch proof. And the negative, how to interpret as a negative result, we'll see in the next slide. Our second result is for the non-interactive setting. We saw that if NP has non-interactive barks, then it also has non-interactive SWI arguments. So like as a consequence, all of these results live to hiding protocols. Yeah, so let's see our results in slightly more details and slightly more formally. So our first result says that batch proofs implies SWI proofs. So what does this mean? So if you have a batch a proof for the batch language LT with compression rate rho, so then it also has honest verified SWI proof and our construction is such that if the starting protocol is well defined, and so is the resulting protocol. And as I said, there are caveats. So let's look at what the caveats are. So soundness-wise, we are good. So our protocol, our resulting SWI protocol has negligible soundness error. So the two caveats are with respect to the WI error and the prover. So the prover we get is not uniform, so it requires some advice. And the WI error we get is not negligible. So it is inverse polynomial. It can be any inverse polynomial if you start with a batch proof that is sufficiently compressing. And thanks to the work of Goldreich, Sai, and Vadan, you can turn this SWI proof into a malicious verifier SWI proof, still with the caveats. So that was our first result. So let's see why this we think of this result as a negative result. So the theorem can be restated as saying if NP doesn't have SWI proofs, then it also doesn't have batch proofs. And so why do we think that NP is likely to have honest verifier SWI proofs, even with the caveats? It has to do with the state of affairs for SDK. So recall that SDK is the set of algorithms that have statistical zero knowledge protocol. So this is a stronger notion of hiding. So it was shown by Fortno and Yellow Herstad that if NP is contained in SDK, then the polynomial hierarchy collapses. So it's unlikely that any NP is contained in SDK. And we believe that SWI should not be more powerful than SDK. So we expect a similar collapse to happen. So yeah, so our main theorem was stated for batch proofs. A similar theorem it extends actually to arguments as well. So you can show that batch arguments imply SWI arguments. And what about the non-interactive setting? So our theorem in the non-interactive setting says non-interactive barg implies non-interactive SWI argument. So more precisely, so if you have a non-interactive batch argument for some NP-complete language that is sufficiently compressing, then you have a non-interactive SWI arguments for any language, any NP language L. So for this transformation, we need dual mode commitments, which is a cryptographic primitive, which is related to commitments. It's a type of commitment which supports both statistical hiding and statistical binding in two modes. So as I said, so this transformation comes without the caveats that we saw before. So we have negligible soundness error, negligible WI error, and our prover is uniform. So by the results of Feigl, Lapidot, and Shamir, so you can turn this non-interactive SWI argument to NI SDK argument. So we essentially show that NI barg implies NI SDK argument, given dual mode commitment. Again, if you are willing to relax the hiding requirement to computational, so suppose you are happy with non-interactive computational WI arguments, so then we can relax the requirement from dual mode commitments to just one-way functions. And again, this can be extended by the FLS result to non-interactive ZK argument. So this result improves on a recent line of work by Champion Wu, Bradley, and Waters, who showed in the end that non-interactive bar for NP and one-way functions give an non-interactive computational zero knowledge argument for NP, just like our statement. However, they rely on stronger notions of soundness than we do. So they require either adaptive soundness or sub-exponential soundness. Okay, so that was our result. So in the last two slides, we will see how we achieve our result, like on a very high level. So for this talk, we will just focus on the proof part, the techniques for the non-interactive setting is mostly similar. If you want to know more about that, you should read the full paper. Okay, so we are given a batch proof, pi equals PV, and we want to construct out of it SWI proof, pi star equals P star V star, where the prover is non-uniform. So like for this talk, we will just make a simplified assumption that pi is non-interactive. So it just sends one message over to the verifier. So the prover P here just sends one message. So you can think of P as being a randomized function. So it's a randomized function which takes as input T instance witness pairs, xi x1w1 up to xtwt, and then it spits out a proof pi. And since we assume that the batch proof is compressing, so the proof is of size rho t. So to extend this result to the interactive setting, it's not very difficult. You just have to fix like the verifier's random points and look at the flattened protocol. So what is the intuition behind this transform? So since P is compressing, it cannot intuitively remember all the witnesses it uses to construct this proof phi. And this is what we will try to formalize into like a witness indexability of phi star. Since the barg is used like in a normal manner, the batch proof is used in a normal manner, so completeness of and soundness of pi star more or less follow from the completeness and soundness of pi. So the most interesting thing to argue here is the hiding. Okay, so we will construct our SWI proof, non-invariant conformer, in 2 steps. So in the first step, we will construct a distributional SWI proof, pi prime equals p prime b prime, given the batch proof. So what is distributional SWI? So recall that SWI, in the definition you saw, it's a worst case notion. So for any x w0 w1, the views of the verifier should be indistinguishable. In distributional SWI, you relax this over distributions over instance witness pairs. So you say that in expectation, with the choice of xw0 w1 over the distribution D, you have SWI. So we will use the batch proof to construct such distributional SWI proofs. So let's see how the construction works. It's pretty natural. So you have the prover P prime and the verifier V prime. They share an instance X, and the prover P prime knows a witness W for this instance X. So the prover P prime wants to use the underlying prover P in some manner. So our idea is to take the instance witness pair and simply embed it into a random position. So recall that the prover P takes T instance witness pairs. So we embed the given instance witness pair in a random location J. So now, so how do we? So we need to select instance witness pair for the rest of the locations. So how do you do it? So you simply sample it independently from the distribution D. So you pick instance witness pairs x1 w10 w11 up to xt wt0 wt1, and then you pass it through the prover, and except for the jth location, they're all passed through. And since the distribution gives you 2 witnesses for each instance, so you need a way to select one of the witnesses. And the way you do it is again simply pick one at random. So the prover first samples this instance witness pairs from the distribution D, and then it tosses a coin B of length T, and simply use it to select one of the witnesses. So this results in a proof phi, and the prover sends the proof phi, the index J, the random location J, along with the instances to the verifier. What does the verifier do? She simply runs the underlying verifier on the underlying batch verifier on the instances that the prover sent, and uses this phi as a proof. And she accepts only if the underlying proof accepts. Yeah, so again, completeness and soundness, they kind of follow. What is interesting is to show that this protocol pi prime is distributional SWI. And to this end, we rely on a compressing lemma of Drucker and Dell. So it's a very useful lemma, and it's useful because of its generality. So it says that for any compressing function G, which takes t-bit inputs and maps it to rho t-bit outputs, these 2 distributions look statistically close. So they are square root rho statistically close, where rho is the compression factor of the function G. So what are these 2 distributions? So on the left, you have the input B, uniformly random input B, which is passed through the function G, where the j bit of the input B is fixed to 0. So this is what this notation means. So on the right, the distribution is the dual. So there you sample a random input B and set the j position to 1 for random j position. And this says that the distribution J and G output of G, where J is fixed to 0, is indistinguishable from J and the output of G, where the J is fixed to 1. So intuitively, it just says that when the function is compressing, then it is and then the output distribution of the function on randomly sampled inputs is insensitive to like random locations. So that is like the intuitive meaning of the lemma. So you can view this pictorially as below. So here you have like randomly sampled B, which is passed through the input to the function G with the jth location set to 0, here set to 1. So we will use this lemma to prove distributional SWI. And the idea is to simply formulate the prover P prime, which we saw in the previous slide, as a function G. So recall that we, for showing distributions of SWI, we need to show that the view of the verifier on the expected distance of the two views is square root rho. And we do this as follows. So recall that the view consists of the instances, the location J, and the proof pi. So this is what the prover P prime sends. And so to show this, you just need to plug in the prover P prime into G. So how do we do this? So the random inputs is the selector bits for the instance witness pairs. Recall that what P prime did was select like T instance witness pairs, and then select the witnesses according to the bit P. So on the left, like in the left, you have the witness corresponding to the jth instance set to 0. So on the left, you always select the witness W0, and on the right, you always select the witness W1. So these two distributions is exactly the distribution in the distributional SWI again. So pi 0 is generated using witness W0, and pi 1 is generated using witness W1. So this almost gives you, so the compression lemma says that J and the distribution of pi 0 is indistinguishable from J and distribution of pi 1. So this almost gives you distributional SWI. You only need to apply the data processing technology to get distributional SWI from the compression lemma. Okay, so what we have shown in the previous step is essentially that for every distribution D, where D is over instance X, W0, W1, so it's instance and pairs of witnesses. So there exists this distribution D bar, where D bar is over T tuples of instance witness pairs, so that these two views are indistinguishable. So what we have showed is that for every D, there exists a D bar, where D bar is, that's essentially the prover strategy of P prime. So to show worst case SWI, so what we want to show, we want to flip the order of quantifiers here. So what we want to show is that there exists a CD so that for any worst case instance XW0, W1, the two views are indistinguishable. And this is this can be shown using Neumann's minimax theorem. So how do you do this? So you can think of the row player, the row player's mixed strategy being over T tuples of instance witness pairs, whereas the column player, the strategy, the mixed strategy is over instance witness pairs. And then you can the payoff of both the players is a zero-sum game, and the payoff is the expected SWI error. So once you frame this problem as a zero-sum game, then you can apply the minimax theorem to flip the order of quantifiers. So since we are planning to provide the distribution D bar as advised to the prover, so we need to invoke the sparse minimax theorem lemma of Plichten and Jung. So this ensures that the description of D bar is not too large. Okay, so that was the how we show our results. So let's wrap up with some open questions. So yeah, so the natural first question to ask is, can we get rid of the two caveats? So for this, you will have to amplify SWI to start with. So this is something we manage for the non-interactive setting. So you can read the paper to see how more, but it's not clear how to use those techniques in the interactive setting. And yeah, so to come up with a uniform prover also seems non-trivial. So like a first hunch would be to use the uniform minimax theorem, but that requires the payoff function to be efficiently computable. So it's not clear how to efficiently compute our payoff function. So there are two hurdles here, and it's not clear how to clear them. And the second open question is to understand SWI as a class. So the sister class of SDK has been well studied by now, but we could define a class SWI, which is like the set of all languages which efficient prover SWI protocols. So does it have a complete problem, for example? And studying the relationship between SWI and SDK is also an interesting avenue to pursue. So that was our paper. So if you want to read more about our paper, you can we have posted it on ECCC and on ePrint. There are also longer format talks available online, so you can check Prashant's talk at Science Institute or my talk at IT Bombay. So yeah, thanks for your attention.